So we'll go ahead and get started here. Today we will be handing out your next set of papers, okay? Not just paper, but papers. It says the second and third one, okay? Because the first one dealt with atomic masses and writing out the compounds. And as we look ahead, when you have these numbers doubled up like this, okay, this would be the 27th, 28th, 29th. So that's when this will be approximately due. But we'll see once how next week rolls out. But we probably stick with Wednesday. Okay, 248. So molecular formulas are very similar to empirical formulas. There's just that extra added step. Okay, at the top, remember that empirical formula contains the smallest possible whole numbers that describe the atomic ratio. The molecular formula is the actual formula of a molecular compound. And empirical formula may or may not be the correct molecular formula. Sometimes they are, sometimes they're not. Okay? For example, dibromane's empirical formula is BH3. Okay? Any multiple of BH3, such as B2H6, B3H9, or B4H12, and so on, as you would guess, is the same ratio of boron atoms to hydrogen atoms. The molecular compounds contain C2H4, cyclopropane, C3H6, also share identical atomic ratios of 2 to 1. They are very different substances. How is the correct formula of a molecular compound found from the empirical formula? The relationship between the compound's empirical formula and its molecular formula can be written as follows. Okay? So you're basically just solving for x. And that's really all that you're doing. Okay? So with this, the number represented by x is a whole number multiple indicating the factor by which the subscripts of empirical formula must be multiplied to obtain the molecular formula. The value of x sometimes is 1. It could also sometimes be 2. It could be up to 3, sometimes even up to 4. Okay? To determine the molecular formula of a compound, you must know the compound's formula mass. For example, experimentation shows the formula mass of dibromane to be 27.67. It says atomic mass units, or we could say grams per mole. The formula mass for the empirical formula is BH3, is 13.84. Dividing the empirical formula mass by the experimental formula by the empirical formula gives the value of x for dibromane. So then, if you determine that the compound has 27.67 as a given information, but the formula you calculate out is 13.84, you just divide those two, and sometimes it's 2, sometimes it's 3, and sometimes it's 1, like we had just read. So the molecular formula for dibromane is therefore B2H6. Okay, so there's some sample problems that you can go through there and read. So we will go ahead and pick number 2 on page 249. It says a sample of a compound with a formula mass of 34 atomic mass units, or we could say grams per mole for our purposes, is found to consist of 0.44 grams of hydrogen and 6.92 grams of oxygen. Find its molecular formula. So when you do this, you have to find the empirical formula first, which we're familiar with because we had done that yesterday. Okay, so 0.44 grams of hydrogen. 0.44 grams of hydrogen. We see a mass. We're probably going to change it to what? We're going to change it to moles. So for every how many moles of hydrogen, what do we have for a mass of it? What is the atomic mass for hydrogen? Okay, so 1.01. Then if we have 6.92 grams of oxygen, how many grams of oxygen would that be? Now, as far as following along with these, sometimes, maybe it's one of those aspects to where, okay, we're just following along in here, and that's fine, because maybe if you look back at what we had done, maybe that doesn't make any sense to you, but this would be the best logical approach, I think, that we could take. What's the atomic mass for oxygen? Okay. So our grams have canceled, we're left with moles. Our grams have canceled here again, we're left with moles. Okay? After class last night, one of my advisors said, for some people, when they get to college, they say, oh my gosh, when we were, how do I want to state this? When it was stressed that we do this dimensional analysis, we hated doing this all the time until we got to college. Now we're in college, and this is easy now, okay? So with that, hopefully we're just putting you that much further ahead of perhaps everybody else. At least that's the goal. So what happens when you divide 0.44 divided by 1.01? And we get what? Well, you get 0.436. We said 3 non-zero digits, so that is moles of hydrogen. Okay, so we do the same thing down here. 6.92. Divide that by 16, and we get 0.433. Again, 3 non-zero digits, moles of oxygen. Now the question is asking for what is the molecular formula. But to do that first, we have to find the empirical formula, just like what we did yesterday. Now that we have this to this point, what is our next step that we would do, if you remember? You divide by the smallest one, so by that case it's this one, but really it's probably not going to matter that much because they are so close in value. But if you wanted to illustrate this, 0.433, and of course 0.433 is just going to give you 1. We know that. And this is going to give you 1. Okay? So upon doing this, we would say, well, does that look right to you? No. Because that is an ion. Okay? So if we just had oxygen and hydrogen, that is just an ion. But there's one critical piece of information that we have not dealt with yet that's in the problem. And that is, it says a sample compound with a formula mass of 34 atomic mass units is found to consist of 0.44 grams of hydrogen and 6.92 grams of oxygen. Find its molecular formula. Well, this is our empirical formula. Okay, but on the prior page, this is what you're essentially doing, is it says that X, excuse me, it says that X times EMF. Now this part, if this might really confuse you, the second part is what I would recommend you write down, because it says EMF, empirical molecular formula, equals the molecular formula mass, I think. We'll just say molecular formula mass. Okay? So how would you get X all by itself? You're going to divide it. Okay? So what that means then, of course, you divide this side by EMF. Okay? They're gone. That now equals X. And that's what they have on that prior page. This is probably what you want to go by. Okay? But it comes from this formula here, what's written in green. So we establish this. We need to find what X is. Because it might be 1, it might be 2, it might be 3, it could be 4. We don't know that yet. But the given information had said the molecular formula mass of this compound was said to be 34. Okay? Because that's given in the problem on page 249. So this number is given in the problem. That's the molecular formula mass. So we had to find our empirical formula, which is right here. But what is the mass of our empirical formula as it sits? What would the 17.01. So approximately, we get pretty close to what number from this when you divide these two? You get X equals 2. So therefore, that means this has to get distributed through the entire compound. So you can write it like this, or you can write H2O2. That is your final answer, H2O2. Okay. Oh, I got those two letters switched around, don't I? Empirical formula mass. So if this is our empirical formula, we add those together, and that's where that number comes from. Okay. Now, did we go through that too quickly? Because if the answer is yes, well then that would indicate to me that we should maybe do another problem. Okay? But then, and I'm not looking out at the audience here, but if we're not going to write this one down, who's going to say we're going to write the next one down? Right? Okay. But we can do the section review on page 249. Okay. It says, if 4.04 grams of nitrogen combined with 11.46 grams of oxygen to produce a compound with a formula mass of 108, we want to say grams per mole, what is the molecular formula of this compound? We would solve this the exact same way we do with this. You have to find the empirical formula first. So we'll go ahead and erase this. Okay. So 4.04 grams of nitrogen, 11.46 grams of oxygen. What's the first thing you think you would do? Find your number of moles. So we will do that first. We've got 4.04 grams of nitrogen. Okay, we're going to change that to moles. Okay, and what is the atomic mass of nitrogen? 14.01. Okay, notice our grams have canceled. We're in moles of nitrogen, and that's what we want. So then oxygen was 11.46. 11 0.46 grams of oxygen. Okay, so for every mole of oxygen, we get 16 grams of oxygen. Okay, then that will give us a number. So this is going to lead us to our empirical formula that we need to find first. Okay, so 4.04 divided by 14.01, that gives us 0.288. Okay, so 0.288, this is moles of nitrogen. Okay, we're going to do the same thing here. 11.46 divided by 16, and then that gives us 0.716. That's moles of oxygen. So we know that this is our formula. We just don't quite know what the ratio is. Yes. Okay. Okay. We need to find our empirical formula. We just know that these two substances are in there. What is our next step? Find your smallest one, which we know this will give you 1. So 0.288. And when we divide that out, 2.465. So this number, okay, we get 1 here and we get 2.465. We can't leave this empirical formula like this. So if we double this, okay, that gives us N2O5. That's still our empirical formula, okay? Then, what did it say in the problem with our molar mass that was given, besides the 4.04 and the 11.46? What else was given? Okay? So therefore, we need to find x, okay? So x is going to equal what was given in the problem as 108. And we've already found our empirical formula. That's right here. But the empirical formula mass, we have to add this together. So we could say 16 times 5 gives you 80. Then the nitrogens, which is 2 of them, 28.02. Okay, that gives us 108.02, which is pretty close to what? 1. So in this case, the empirical formula and the molecular formula were the same. Unlike the last problem we did, it came out to that because you had to double it. Here we don't have to because it's pretty close to 1. The other example was 34 divided by 17.01, and that equaled 2. That's why you had to double that. Okay, so before some of you leave here,
So what's our answer on that one?
N2O5. You know, why don't I just hang on to these, because I highly, highly doubt we're going to work on these on the weekend, because I probably wouldn't either. Okay. But who works on a Friday night?
Me. Where did you get 5 from?
Okay. Where did this 5 come from?
I think I got it.
Because this was pretty close to 2.5, okay? But we can't have NO2 2.465, or N 2.5. So we double that, that gives us 5, that gives us 2. That's where those numbers come from. Okay? And I don't think we would have time to do another one, but if we went really, really fast, we probably could. Yes? Yes. Take your stuff with you, because we'll probably be out of here in a few minutes anyway. So, front row, are we on the bus here? Yes? And before we leave, are we on the bus? Yep. Okay, back row, are we on the bus? Okay. We will catch up to you next time.